correct sizing of the grounding conductor between a transformer and a panel depends on the specific National Electrical Code, or NEC, code cycle and the system configuration. In the 2005 NEC and earlier, the grounding conductor was referred to as the equipment grounding conductor and was sized according to section 250.122. However, in the 2008 NEC and later, the grounding conductor is now referred to as the system grounding conductor and is sized according to section 250.66. There are some exceptions to the general rule of sizing the grounding conductor according to 250.66. For example, for a solidly grounded system, the grounding conductor does not need to be larger than the largest phase conductor. For a resistance grounded or impedance grounded system, the grounding conductor must be at least as large as the largest ungrounded phase conductor, but not smaller than the minimum size specified in Table 250.66. If you have sized the grounding conductor as an equipment grounding conductor per 250.122 for over 20 years, this is consistent with the requirements of the NEC codes up to 2005. It's important to note that the NEC code has been updated since then, and the sizing of the grounding conductor is now specified in section 250.66. Therefore, you should review your designs and ensure that they are in compliance with the current NEC code cycle. It is recommended to consult with a qualified electrician or electrical engineer for specific guidance on the sizing and installation of grounding conductors. Section 250.66 provides the requirements for sizing the system grounding conductor for alternating current systems. The size of the system grounding conductor is based on the size of the service entrance conductors. If the service entrance conductors are paralleled into or more cables or raceways, the equipment grounding conductor shall be sized as if the service entrance conductors were installed in a single cable or raceway. The minimum size of the grounding electrode conductor is given in Table 250.66, which is based on the size of the service entrance conductors or the equivalent area for parallel conductors. Section 250.122 covers the sizing of equipment grounding conductors. The size of the equipment grounding conductor is based on the rating of the overcurrent protective device protecting the circuit. Table 250.122 provides the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device. When conductors are adjusted in size to compensate for voltage drop, equipment grounding conductors must be adjusted proportionally in size as well, according to 250.122b. If multiple circuits are installed in the same raceway, cable, or enclosure, single equipment grounding conductor sized according to the largest overcurrent protective device is adequate for all circuits. For example, consider 480 volt to 208/120 volt transformer serving a panel. If you were following the 2005 NEC, you would have sized the grounding conductor from the transformer to the panel as an equipment grounding conductor per 250.122. based on the overcurrent protection device for the transformer secondary conductors. However, under the 2008 NEC and later, you would size it as a system grounding conductor per 250.66, based on the size of the transformer secondary conductors. Let's consider a specific example. Suppose you have a transformer with 500 kV ampere rating, stepping down 480 volts to 208/120 volts. Assume the transformer secondary conductors are sized at 1250 amps. Using the 2005 NEC, you would refer to Table 250.122 to size the equipment grounding conductor. If the overcurrent protection device is rated at 1200 amps, you would need a number 3/0 American wire gauge copper conductor or a 250 kcal aluminum conductor for the equipment grounding conductor. With the 2008 NEC and later, you would size the system grounding conductor according to Table 250.66 based on the size of the transformer secondary conductors. For 1250 amp conductors, you would typically need a number 3/0 American wire gauge copper conductor or 250 kcal aluminum conductor for the system grounding conductor. In both cases, for this specific example, the size may end up being the same, but the method of determining the size and the applicable NEC section are different. The equipment grounding conductor ensures a low impedance path for fault current back to the source, facilitating the operation of the overcurrent protective device. The system grounding conductor connects the neutral point of a transformer or generator to ground, stabilizing the voltage and providing a reference point for the electrical system. Grounding is essential for safety and proper operation of electrical systems. It provides a low impedance path for fault currents, protecting equipment and personnel from electrical shock hazards. Grounding also helps to stabilize voltage levels and reduce electrical noise, which can improve the performance of sensitive electronic equipment. Always consult the latest edition of the NEC and local amendments for the most accurate and up-to-date requirements. Also, always consult with a qualified electrical engineer or licensed electrician to ensure that the grounding system is properly designed and installed. It is important to understand the difference between the equipment grounding conductor and the system grounding conductor and to size them correctly based on the relevant NEC requirements. An equipment grounding conductor connects non-current carrying metal parts of equipment, raceways, and enclosures to the system grounding point, ensuring a low impedance path for fault current back to the source. Its purpose is to provide a path for fault current to flow back to the source, allowing overcurrent protective devices to quickly trip and clear the fault. The system grounding conductor, on the other hand, connects the neutral point of a transformer or generator to the grounding electrode system. Its purpose is to stabilize the voltage to ground and provide a reference point for the electrical system. A properly sized system grounding conductor helps to limit voltage fluctuations and prevent overvoltages that could damage equipment. The NEC specifies different sizing requirements for these two types of grounding conductors. The equipment grounding conductor is sized based on the rating of the overcurrent protective device protecting the circuit, while the system grounding conductor is sized based on the size of the service entrance conductors or the derived and grounded conductors from a separately derived system like a transformer. It is also important to consider any applicable exceptions or special rules that may apply to specific situations. For example, the NEC permits the use of smaller equipment grounding conductors in certain cases, such as when they are installed in cable trays or when they are supplemented by other grounding means. The grounding electrode conductor connects the grounding electrode system to the equipment grounding conductor, the system grounding conductor, or both, at the service equipment or at the source of a separately derived system. The grounding electrode conductor is sized according to NEC Table 250.66. Based on the size of the service entrance conductors or the derived and grounded conductors from a separately derived system. The grounding electrode system consists of one or more grounding electrodes that are bonded together to form a low impedance connection to the earth. Common types of grounding electrodes include metal underground water pipes, metal frames of buildings, concrete encased electrodes, and ground rods. The NEC specifies minimum requirements for the size and type of grounding electrodes. In addition to the NEC requirements, local codes and regulations may also have specific requirements for grounding systems. It is essential to consult with local authorities to ensure that the grounding system complies with all applicable codes and regulations. Proper grounding is crucial for electrical safety and equipment protection. A well-designed and properly installed grounding system provides a low impedance path for fault currents, minimizing the risk of electrical shock and equipment damage. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Check for loose connections, corrosion, and other signs of damage. Test the grounding system periodically to verify its integrity and effectiveness. Grounding systems can be complex, and it is important to have a thorough understanding of the NEC requirements and best practices for grounding. Seek out training and educational opportunities to enhance your knowledge and skills in this area. Remember, proper grounding is not just a code requirement, it is a critical safety measure that protects people and equipment from electrical hazards. Ensuring a safe electrical system is a shared responsibility. By following the NEC requirements, adhering to best practices, and staying informed about the latest developments in grounding technology, you can contribute to a safer electrical environment for everyone. Understanding the terminology used in the NEC is crucial for accurately interpreting and applying the code requirements. Grounded conductor means a system or circuit conductor that is intentionally grounded. Grounding conductor means a conductor used to connect equipment or the grounded circuit of a wiring system to a grounding electrode or electrodes. Grounding electrode conductor means the conductor used to connect the grounding electrode to the equipment grounding conductor, to the grounded conductor, or to both, of the circuit of the service equipment or at the source of a separately derived system. Bonding jumper means a reliable conductor to ensure the required electrical conductivity between metal parts required to be electrically connected. Separately derived system means an electrical source, other than a service, that has no direct electrical connection to circuit conductors of any other electrical source other than those established by grounding and bonding connections. Common examples of separately derived systems include transformers, generators, and solar inverters. Impedance grounded system means a grounding system in which the grounding impedance is deliberately inserted in the grounding circuit to limit the flow of fault current. Resistance grounded system means a system of grounding in which a resistor is inserted in the grounding circuit to limit the flow of fault current. Solidly grounded system means a grounding system in which the neutral point of a transformer or generator is directly connected to ground without any intentional impedance. Voltage drop calculations are essential for ensuring that electrical equipment receives the proper voltage for safe and efficient operation. The NEC recommends limiting voltage drop on feeder and branch circuits to no more than 3% to the furthest outlet for power, heating, and lighting loads, or combinations of these. The total voltage drop on both the feeder and branch circuit to the furthest outlet should not exceed 5%. Excessive voltage drop can cause equipment to malfunction, overheat, and fail prematurely. It can also result in reduced lighting output and decreased motor performance. To calculate voltage drop, you need to know the following information: conductor size, conductor length, conductor material, circuit current voltage, and power factor. Several online voltage drop calculators are available to assist with these calculations. These calculators typically require you to input the information listed above and then provide you with the calculated voltage drop. When sizing conductors, it is important to consider not only the ampacity of the conductor but also the voltage drop. In some cases, you may need to increase the conductor size to reduce voltage drop to an acceptable level, even if the conductor is already adequately sized for ampacity. Understanding and applying the NEC requirements for grounding and voltage drop is essential for ensuring the safety and reliability of electrical systems.